Okay, this is the last video about magnetostatics. We're going to look at two things called solenoids and toroids. And a solenoid is something you've seen before. It's basically a coil of wire. So you have, and it carries a current. And so each one of these loops of wire carries a current I. And if you draw what the magnetic field looks like, the field inside the solenoid will be given by the right-hand rule, so you curl your fingers in the direction of the current, and your thumb, in this case, points in that direction. So the field for this solenoid points to the left inside it, and will loop around the outside. Now, the equations we're going to derive are for an infinite solenoid, which in practice means a solenoid that's longer than it is wide. And because it's infinite, it has an infinite number of turns, but it has n turns per unit length. So if we have a very long solenoid, little n equals the total number of turns divided by the length of the solenoid. But we're just going to look at a portion of the infinite solenoid. And if the solenoid is infinite, what that means is that none of these lines that loop around the outside actually make it back. So when we have an infinite solenoid, the magnetic field is 0 outside the solenoid, and it's constant inside the solenoid, or uniform rather. So if we draw a portion of the cross-section, we have a bunch of wires carrying currents into the page up here, and wires carrying currents out of the page down here. The magnetic field is uniform inside the solenoid, 0 outside of it. In order to calculate the field, we're going to use an Amperian loop that's rectangular in shape, has length little l, and we're going to go around it in that direction. Amperes Law says B dot ds integrated around the loop equals mu naught times the enclosed current. Now the first thing is to notice that the magnetic field being 0 outside the solenoid means that the top part of our loop makes no contribution to B dot ds, because B equals 0 out here. And then for the two vertical sides, yes, part of them are inside the solenoid, and so B isn't 0 along them, but B is perpendicular to ds, and so for these two sides, B dot ds is equal to 0 even if B isn't. And that means that all of the contribution to the line integral comes from the bottom edge. And the line integral just equals B times L. The enclosed charge, or the enclosed current, is equal to the number of wires inside the loop times the current in each one. But the number of wires equals the number of wires per unit length times the length. And that means that L, the length of our Amperian loop, cancels out of the equation, and we're left with our final equation, B equals mu naught In. May or may not be worth memorizing that, but you definitely need to be able to derive it. Notice that the only thing that matters is the current in the solenoid and the density of the wires, how close they're packed, how many of them fit in a particular unit length. Radius of the solenoid doesn't matter, length of the solenoid doesn't matter, as long as the length of the solenoid is long compared to the radius. And the second thing we're going to look at is a toroid, where you imagine a solenoid bent into a donut shape. And it's really, really hard to draw, so I'm just going to draw a cross-section of it. You have an outer circle, you have an inner circle, and you basically have along the inner circle a bunch of wires that carry current out of the page And along the outer circle, you have a bunch of wires that carry current into the page. Toroids are actually quite useful because, as we'll see, they allow no magnetic field to leak outside. The magnetic field circulates entirely inside the toroid. And we can also say that there are capital N turns. We're generally going to use capital N for the total number of turns, little n for the turns per unit length. The magnetic field of this toroid will look like this. And the field is 0 inside here, and also 0 outside here. All of it stays there. When you're designing electronics, you don't want stray fields, and so when you need something called inductors, those are usually bent into toroid shapes. We'll learn about inductors in the next chapter. What we'll do is we'll draw an Amperian loop of radius little r somewhere between the inner and outer radii of the toroid. Amperes Law says B dot ds equals mu naught I enclosed. Now, because the magnetic field always points the same way as ds, B dot ds just equals the length of the loop, 2 pi r times b. Mu naught is a constant, and the enclosed current is just the number of loops times the current in each one, because all of the loops, or all of the turns in the toroid, end up going through the interior of the Amperian loop. So it's I times capital N. Rearranging that gives us B equals mu naught IN over 2 pi r. And that, of course, is if r is within the toroid. If r is either smaller than the inner radius or larger than the outer radius, B is equal to 0. Again, not something you probably need to memorize, but something you need to be able to derive. And tomorrow I'm going to check problems 41 and 43, and they're not actually too terribly difficult. There's not too many difficult questions they can ask you about solenoids and toroids with the kind of math that you know. And that brings us to the end of magnetostatics. We have one more chapter to go, and that is magnetic induction.